of chromyl chloride are formed. When these vapors are passed into NaOH solution, it turns yellow due to the formation of Na2CrO4. Acidified solution of dichromate ions forms deep blue color with H2O2 due to formation of CrO5 CrOO2. Interconversion of chromate into dichromate. Chromate ion is tetrahedral, whereas the dichromate ion consists of two tetrahedra sharing one corner with chromium-oxygen-chromium bond angle of 126 degree. There is an equilibrium between chromate and dichromate ions at a pH of about 4. They are interconvertible in aqueous solution depending upon the pH of solution. Chromate ions change into dichromate ions on adding acid, while dichromate ions change into chromate ions on adding alkali. Oxidation state of chromium is dichromate and chromate is same. Potassium permanganate, KMnO4. Potassium permanganate is an inorganic chemical compound with the formula KMnO4. It is a salt consisting of K positive and MnO4 negative ions. It is obtained from pyrolurite, a black color powder. Pyrolurite is fused with KOH and air. This produces a green color potassium manganate. Commercially, it is prepared by an electrolytic oxidation of an aqueous solution of K2MnO4. Manganate and permanganate ions both are tetrahedral. Green manganate is paramagnetic with one unpaired electron, but purple permanganate is diamagnetic. Properties of potassium permanganate. Potassium permanganate is purple-black colored crystalline solid with a melting point of 523 Kelvin. It is soluble in water. Its aqueous solution has purple color if concentrated, but if the solution is dilute, it has pink color. On strong heating, it decomposes to give oxygen. On heating with alkali, potassium permanganate changes into potassium manganate and oxygen gas is evolved. It is a very strong oxidizing agent in both alkaline and acidic medium. Uses of potassium permanganate. The important uses of potassium permanganate are following. It is used as a disinfectant and germicide. A very dilute solution of KMnO4 is used for washing wounds. It is used as an oxidizing agent in laboratory and industry. It is used as oxidant in preparative organic chemistry and as Beer's reagent. It is used for purifying water of stinking wells. It is used in the volumetric estimation of ferrous salts, oxalic acid and oxalates. F-block elements, the inner transition elements. In F-block elements, the last electron enters the anti-penultimate energy level, that is n-2 f orbitals, where n can be 6 or 7. The last electron also called as differentiating electron. These elements are also called inner transition elements because n-2 f orbitals lie deep within, inner to the penultimate shell. The general electronic configuration of these elements is n-2 f1 to 14, n-1 d0 to 1, ns2. The inner transition elements have been divided into two series, lanthanoids and actinoids depending upon the fact that whether the differentiating electron enters a 4f orbital or a 5f orbital. The lanthanoids. When differentiating electron enters one of the 4f orbital, the element is said to be belonging to the first series of inner transition elements. 14 elements after lanthanum belong to this series. These are called lanthanoids as they appear immediately after lanthanum in the periodic table. The atoms of these elements have electronic configuration with 6s2 common but with variable occupancy of 4f level. It is energetically favorable to move single Fd electron into 4f level in most of the elements. Cerium, gadolinium and lutetium has 5d1 arrangement because they leave a half-filled 4f level which gives increased stability. Physical properties of lanthanoids. All lanthanoids are soft and silvery white metals. Some properties of lanthanoids are following. Color. Many trivalent lanthanoid ions, Ln3+, are colored both in the solid state and aqueous solution. The color seems to depend on the number of unpaired F electrons and arises from F to F transitions. For example, Pr3+ is green and Pm3+ is pink. Density. Lanthanides have high densities ranging from 6.77 to 9.74 gram per centimeter cube. It increases with increase in atomic number. Melting points and boiling points. Lanthanides have fairly high melting points and boiling points, and these increase with increase in atomic number. This is because the attraction between atoms increases as the size decreases. Chemical properties of lanthanoids. Oxidation state. The sum of first three ionization energies is low, and therefore the most common and stable oxidation state is +3. Magnetic behavior. Ln3+ ions are generally paramagnetic due to the presence of unpaired electrons in f orbitals. La3+ and Ce4+ have an F0 configuration and Lu3+ has an F14 configuration, therefore they are diamagnetic. Chemical behavior. Early members of the series are quite reactive, similar to calcium, but with increasing atomic number, they behave more like aluminium. Lanthanoid contraction. The atomic radii and ionic radii of tripositive lanthanoid ions show a gradual decrease down the group. Although the atomic radii show some irregularity, but ionic radii steadily decreases down the group. The additive effect of contraction over 14 lanthanoid elements is quite appreciable. This is known as lanthanoid contraction. As the atomic number increases in lanthanide series, for every proton added to the nucleus, the extra electron goes to fill 4f orbitals. 4f electrons constitute inner shells and therefore are not so effective in shielding the nuclear charge. Therefore, electrons are pulled closer to the nucleus due to shrinking of electron cloud. This results in gradual decrease in size of lanthanoids with increase in atomic number. Uses of lanthanoids. These metals are not much used. The important uses of lanthanoids are following. The unseparated mixture of lanthanum and lanthanides is called mixed metal. It contains about 50% cerium, 40% lanthanum, 7% iron and 3% other metals. This is added to steel to improve its strength and workability. Mixed metal is also used in small amounts as lighter flints. La2O3 is used in Crookes lenses which give protection from ultraviolet light by absorbing it. CeO2 is used to polish glass. CeSO4 2 is used as an oxidizing agent in volumetric analysis. The actinoids. The series of elements involving the filling of 5f orbitals is called actinoid series. They follow actinium and include the 14 elements from thorium to lawrencium. They are so called because they come immediately after actinium in periodic table. They are also known as second inner transition series. They have electronic configuration of 7s2 and variable occupancy of 5f and 6d subshells. The actinoids are radioactive elements. The earlier members have relatively long half-lives and the latter ones have half-life values ranging from 1 day to 3 minutes. Properties of actinoids. All actinoids are silvery white metals. These elements are radioactive. After uranium, all the elements are man-made. They have high densities. Their melting points are moderately high but are considerably lower than those for transition elements. Ionic size. The size of ion decreases regularly along the series because the nucleus is poorly shielded by f electrons. This is known as actinide contraction. Oxidation state of actinoids. They have an oxidation state of +3. However, this is not always the most stable oxidation state in them. The most stable oxidation states for the first 4 elements are thorium +4, protactinium +5, uranium +6, and neptunium +5. Plutonium shows all oxidation states from +3 to +7, but the most stable is plutonium +4. For americium and the remaining actinides, +3 is the most stable oxidation state. Uses of actinoids. The important uses of actinoids are following. Thorium is used in atomic reactors to generate power. Thorium is also used in the treatment of cancer. Uranium is used as nuclear fuel in reactors. Uranium salts are used to impart green color to glass. Plutonium is used as fuel in atomic reactors and also for making atom bombs. Difference between lanthanoids and actinoids. In lanthanoids, last electron enters into 4f orbital, whereas in actinoids, last electron enters into 5f orbital. In lanthanoids, general electronic configuration is 4f0 to 14,5d0 to 16s2, whereas in actinoids, general electronic configuration is 5f0 to 14,6d0 to 17s2. In lanthanoids, the decrease in atomic size is not regular, but the decrease in size of tripositive ion is regular. Whereas in actinoids, there is gradual decrease in the atomic and ionic size. In lanthanoids, the principal and common oxidation state is +3. Some elements also show +2 and +4 oxidation states. Whereas in actinoids, the common oxidation state is +3, but it is not always the stable state. Lanthanoids do not form complexes readily, whereas actinoids have much greater tendency to form complexes. Compounds of lanthanoids are less basic, whereas compounds of actinoids are more basic. Lanthanoids are non-radioactive except promethium, whereas actinoids are all radioactive. Did you know Iron was believed to have been first discovered by the Egyptians in 4000 BC. The widespread use of this element led to the period in world history called the Iron Age. The term carat, meaning purity, is used to indicate the amount of gold present, with 24 carats being pure gold and lower ratings proportionally less. Henry Antoine Becquerel discovered that uranium was radioactive in 1896. Summary. Let us summarize what we have learned. The d block elements are those in which last electron enters the d subshell of penultimate shell. Atomic radii of transition elements in a period smaller than s block elements and larger than p block elements. In a particular transition series, ionization energy increases gradually as we move from left to right. Electrode potential is the electric potential developed on a metal electrode when it is in equilibrium with a solution of its ions, taking electrons from the electrode. The transition metal ions generally contain one or more unpaired electrons in them, and hence their complexes are generally paramagnetic. Potassium permanganate is obtained from pyrrolurite, a black color powder. Pyrrolurite is fused with KOH and air. This produces a green color potassium manganate. The series of elements in which differentiating electron enters one of the 4f orbital are known as lanthanoids. The series of elements involving the filling of 5f orbitals is called actinoid series.